three possible meanings for such a sentence. First of all, it may mean that the task must be performed by a set of exactly two users, and both of them must be are accountants. In the second meaning, that it requires a set that contains two accountants, but the set can contain any other additional users. And in the third meaning, the policy requires a group of accountants, and there must be at least two of them. So if we design the term satisfaction to be monotonic, then we cannot capture the first and the third meaning. And our current definition of term satisfaction can capture all the three meanings, all the three different meanings of the policy. So you may wonder how to use the algebra to specify high-level policy. So a policy associates a sensitive task with a term specified in the algebra. So for example, the policy in the example associates a term with a task on issuing checks. It means that the task to issue a check requires a set of three users containing a manager and two clerks. So after introducing the syntax and semantics of the algebra, we would like to talk about two computational problems related to the algebra. So the first problem is the term satisfiability problem. So given a term, we would like to determine whether there exists a configuration and a user set such that the user set satisfies the term under the configuration. The intuition is that if we have a term that cannot be satisfied by any user set under any configuration, then probably such a term is not meaningful and is not what the designer wants. One example of a term that is not satisfiable is a term that uses square cap to connect a row R and the negation of row R. Such a term requires a user who is a member of row R and not a member of row R, and such a term cannot be satisfied. And of course, there are more complicated terms that cannot be satisfied, and we would like to determine such case. And the other problem is the user-term satisfaction problem. So given a term and a configuration and a user set, the problem determines whether we are asked whether the user set satisfies a term. So intuitively, a term under given a configuration, a term defines a set of user sets. So such a problem asks whether a given user set is in this set of user sets or not. We have studied the computational complexity of both problems, and we show that the term satisfiability problem is NP-hard even if the term use only rows and three operators, which are negation, square cap, and square cap. The problem is still NP-hard even if the terms only use the atomic term in the form of set of users and operators square cap, and O dot. The problem is NP-complete in general, but it can be solved in polynomial time if the term does not contain negation and atomic terms in the form of set of users. And we have also studied the computational complexity of the user-set-term satisfaction problem, and we show that the problem is NP-complete in general. And we have also studied the subcases of the problem in which only a subset of the 6 operators can be used. So here is a diagram that shows all the computational complexity results we have. And as we can see, if the operators in the bracket means the operators that can be used in the term in the case we consider. So if the term does not use operator O dot and O time, then the user term satisfaction problem can be determined in polynomial time. Otherwise, as long as O dot or O times is used with any other binary operators, the problems becomes NP complete. So the user term satisfaction problem is NP hard means that there exist cases that require exponential time to solve the problem. However, in practice, the instances we encounter in practice we may still be able to solve them efficiently. In order to check whether how efficient we can solve the problem in practice, we design and implement an algorithm for the user term satisfaction problem. Our algorithm contains 2 procedures. In the bottom-up processing, we try to enumerate all the set of users that satisfy. We first build a syntax tree for a term, and all the leaf nodes in the syntax tree represents an atomic term, and we try to enumerate all the set of users that satisfy this atomic term and compute the satisfaction set from bottom up. And in the top-down processing, we try to split the user set into different subsets and try to see whether those subsets satisfy the branches of the syntax tree. And our experimental results shows that such an algorithm can solve general cases of reasonably large size within a quarter of a second. So can be solved pretty efficiently. So next, I would like to discuss the relation between our algebra and regular expressions. As we have seen, a term in an algebra defines a set of sets, and regular expressions, which is widely used, defines a set of strings. So there are similarities between these two. And as we can see in the example, the regular expression defines a set of strings such that each string in the set starts with the character A and followed by the character B or C